In this video, I would discuss one of the most fascinating abstractions that we study in function analysis, and that is of a sequence space. What is a sequence space? Now, if we come to think of it, a sequence space X is a metric space such that every point, so every element which belongs to this metric space is an infinite sequence. So these sequence spaces have different kinds of metrics defined on them. They have different kinds of norms associated with them, and hence they have different types of nature. So first we consider our sequence space L infinity, which is the space of all bounded functions. Sorry, the space of all bounded sequences. Space of all bounded sequences. So L infinity is the space of all bounded sequences. And what do I mean by a bounded sequence? So I mean that if I have a sequence X, okay, which can be represented as this, like an infinite sequence, then every individual element of that sequence has this norm which is bounded by a number Cx, which depends upon my x. So let's think of it again. So I have an infinite sequence, okay, and the property of this infinite sequence is such that every element is bounded. So out of all the elements here, even the maximum of it is bounded. So for all j equals to 1, 2, and when my sequence satisfies this property, I call it L infinity sequence, and the metric defined on this metric space of all bounded sequence is like this. So when I talk about a metric defined on a sequence space, I mean that the supremum norm over index j for all my ej's minus neta j. And what is this neta j? Consider a y, which is another sequence in my sequence space, denoted like this. So when I take the distance between this sequence and this sequence, or let me put it more precisely, when I take the metric between x and y, where x and y are elements of my metric space x is such that every element is a bounded sequence, then this is how I give the metric. So that's the concept behind sequence spaces.